and talk a little bit about the work that we have been doing for about 3 years in my group now. And hopefully I can get the presentation to come up here in a second. There we go. So the title of my talk is Nanomaterial Catalyst for Solar Hydrogen Generation. And it's basically about taking solar energy and converting it into fuel. And one very popular fuel these days is hydrogen, because hydrogen is does not have any adverse effects on the atmosphere and climate change, and it can be generated from water quite easily. And so basically the idea is to make a catalyst that you immerse in water, shine light on it, and then have the catalyst split the water into hydrogen and oxygen. And this could look like this. Some of the videos not starting, maybe I just need to click on it. Could look like that. Basically here you have the powder catalyst on the bottom in this flask, shine light on it, and then the water is split into hydrogen and oxygen gas. And that is an endothermic reaction. It's an uphill reaction, and these gases are energy rich and can be converted back into water. And that energy can be used to heat, or the energy could be used to drive a piston in an engine. Or one could also think about using hydrogen and oxygen and run it through a fuel cell and generate electricity that way. So it turns out that the idea of using catalysts for water splitting is fairly old. The original key discovery was made in Japan by Akira Fujishima, who found that if you illuminate titania in the presence of water with ultraviolet light, then water splitting can happen. And a few years later, people discovered that you can actually do this in a self-supported catalyst as well. Basically, such a catalyst is shown schematically here. It's a TiO2 powder. Titania is fairly ubiquitous. It's in your toothpaste and probably some in the creamer here as well. It's a white pigment. And if you fuse it to a platinum nanoparticle or platinum metal, then you can have a catalyst for water splitting. Basically, if you shine light on this, what happens is that the TiO2 produces an electron-hole pair. Then the electron is given to the platinum particle, which can use it as a reducing equivalent to turn protons into hydrogen gas. And the hole is used on the other side to oxidize water into oxygen. So basically, the catalyst has several functions here. One is it absorbs the light. Another one, it separates the electron-hole pair at the platinum-titania interface. Then it reduces the protons on the platinum surface, and it oxidizes the water there. All parts are combined in this catalyst. So there are over 130 known compound semiconductors that can do the overall water splitting reaction or parts of it. But there's not a single catalyst that does this with an efficiency of greater than 1%. And I'm speaking about the overall water splitting reaction. So there's a big demand there to improve catalysts and understand the mechanism better and to enhance efficiency. In general, people say that you want 10% efficiency in order to make a commercially viable system there. So a lot of work has been done in this area over the last 40 years, but there's still no very fundamental understanding about the porosity that affect the efficiency of these catalysts. And one of the reasons for that is that most of these materials are bulk materials, and depending on the synthetic conditions, they can have impurities, they can have different surfaces exposed, and so it's very difficult to study this in a systematic way. So we're trying to learn about water splitting using nano crystals as catalysts, and we're taking advantage of the fact that these nanocrystals are often very pure, they have very well-defined surfaces, they are soluble in water, and they can be studied using spectroscopic techniques. Then in addition to that, they also have a very small size, so when we generate these electron-hole pairs in the interior, they can easily migrate to the surface without decaying. That should enhance the efficiency of this catalyst. But then we also have some problems of these nanocrystals. And one problem is that because they're so small, it is very difficult to separate the charges in these crystals because the charges are always very close to each other. So there have to be ways invented to facilitate the charge separation. Another effect Dong-Yu spoke about is also quantum size effects. Quantum size effects allow us to tailor the band structure of these catalysts. So I'd like to briefly talk about one material that we have been looking at, which to my knowledge is the first material where a quantum size confinement effect has been used to activate this material for water splitting. And this material is cadmium selenide, very well known in the community for fundamental studies on quantum size effects. It has a band gap of 1.7 eV, so it absorbs visible light. However, when you put it into water and shine light on it, it does not produce any hydrogen. On the other hand, cadmium sulfide, which is related, has the same Woodside type structure, does produce hydrogen when irradiated in water. And it can do that because its band gap is larger, and so the electrons are more reducing in this material when it's being illuminated. So we have been thinking that we might be able to activate the cadmium selenide by making a nanoscale version of it, thereby enhancing its band gap using the quantum size confinement effect. We can make cadmium selenide nanoribbons very easily following a literature procedure where we mix cadmium chloride, octylamine, and selenocarbamate at 120 degrees. And if this is done under the proper conditions, then you get cadmium selenide nanoribbons that precipitate from the solution as a yellow powder. From electron microscopy, we know that these ribbons are basically form stacks to form these elongated structures. And in each of these elongated structures, you basically have many stacks of the Woodside type cadmium selenide crystal lattice stacked on top of each other. Each of these slabs in there is only 1.5 nanometers thick, which causes the quantum size confinement effect in this material. When we look at the optical characteristics of this material, we see that in contrast to regular cadmium selenide, which absorbs all the way down to 700 nanometers, this one only absorbs down to 450 nanometers, and it has two distinct absorption bands there, another one at 425 nanometers. This is a direct consequence of the phenomenon that Dong-Yu just spoke about, that the quantum size confinement effect spreads the energy levels that are allowed and that can be occupied, and that leads to these discrete absorptions in this material. Here's also a picture. You see the yellow material there. Now, in order to test it for water splitting, we take a suspension of this material in water, and then we put it into a chemical reactor that is illuminated with several lamps here. And we have a better photoreactor now, but I'm just showing the old one here, which we used for a long time and served our purpose as well. It's constructed out of 4 mercury lamps from Home Depot for $30 a piece. So you can actually do chemistry with relatively little money investment. So the catalyst mixture is in this flask. On top is the gas space to accumulate the gases. And then we take samples with a gas chromatograph out to analyze for hydrogen content. We know roughly how many photons these lamps produce using chemical test reactions, and with that we can determine that we get about 0.6 micromoles of photons per second that arrive in the flask. That is very important to know if you want to determine the efficiency of your catalyst, how many photons make it into the reaction flask. So if we illuminate this, indeed, some hydrogen gets formed, and you see that here after about 300 minutes, maybe 20 micromoles of hydrogen. That is a very, very small amount. That's like less than 0.1 milliliters of hydrogen. So we have wasted a lot of energy making this here, but we have shown that we can form some hydrogen that way. Unfortunately,